All right, so what we're going to talk about today is just a continuation of what we had last time, um, getting onto kind of the opposite of what we talked about. So last time we were talking about emissivity, which was the amount of light that a source could put off and the amount that it could absorb, basically, which we found out whatever light it can absorb is what it can emit. And here we're going to talk about, at least to start, something called albedo. And this we're going to define as the power scattered. So scattered by something, usually a gas or something. So power scattered divided by the amount of incident power. So in other words, we shine a bunch of light on it. That's our incident power, a bunch of radiation on it. And then we look at how much of it is absorbed and throw that out, and we look at just what part of it is re-emitted back out. It's scattered. It goes in, it's absorbed, and then re-scattered back out in different directions. And then we would divide those numbers, the amount that gets scattered all over the place, or what was totally in, and we would get this. Basically, what you're looking at is kind of another way to think about it. Since emissivity was what was absorbed, this is basically what's not absorbed over the incident power. So, whatever's incident on it, whatever's not of that is absorbed, is what that would be. Since this is basically the opposite of the other, it turns out that albedo plus emissivity equals 1, or 100%, because they're kind of the opposite of it. One is what's absorbed, one's what's not absorbed, but rather scattered. And when I say scattered, what I mean is when the light rays come in, the radiation comes in, and it hits a molecule. So if some atom or something here, this light ray comes in and hits it, it can actually has the potential to be shot out in all different directions. So it might come in, and one time it might shoot off this way, another time it might shoot off that way, or this way, or really just any direction. It can go right back, it could go forward, it can go up this way, and it just basically can be scattered in all directions. So if we send a bunch of light into like a gas of all these atoms, what'll happen is you'll get this scattering where it'll end up being that it shoots out in all directions. So that'll be kind of important to what we talk about in a little bit. So remember, this is what's scattered, this is what can be absorbed, okay? And so it has to be one or the other. Next thing is the solar constant. I want to put the word constant in parentheses because it isn't constant, it's just close to being constant. And what the solar constant is our average. It's our average thermal energy per unit area incident upon Earth, and that's coming from the sun. So average thermal energy per unit area incident upon Earth. Okay, so if we look at that, we would, you'd go up in the air and you'd find, like, say it was we're looking, our unit area was meter squared. You'd look at Earth and its atmosphere. You'd say, oh, okay, here's Earth, and its atmosphere is real thin, just right around it, not much of a addition to the radius. And you'd come in and look and say, all right, here's a square meter, and then I would measure how much actual radiation was coming in, how much thermal energy from the sun, because that's where we get our heat, right? We talked about that in the last one, would come in and actually hit that little square, and that would be that. And this is our solar constant, our average unit area, or average thermal energy per unit area incident upon Earth. It is approximately, although it varies around below this number, depending upon the activity of the sun. More sunspots, the higher this number gets. The less sunspots, the less activity, the lower this number gets. Is 1.4 kilowatts per square meter. Okay, and that's approximately its value right there. All right. Next thing to talk about is what determines the albedo of Earth. So a couple things that can affect it, and some other things is really just what's it made out of? What's that material? It's kind of a material property like emissivity is. In fact, it's if you find the emissivity, you already know the albedo because all you have to do is subtract this from 1. 1 minus emissivity is albedo. So the albedo is based on the emissivity, and the emissivity is based on albedo, back and forth. You kind of have, no matter what you're given, you always have the other. You just have to subtract what you're given from one, and then you suddenly have the other one. So for this, it's a material property. So for Earth, some of the things that can have a big effect on it would be the amount of snow or snow cover on the planet. If we had snow, more snow cover on the poles, well, snow shines light back up. It's very reflective. It's white. So light coming in would be reflected back, which would mean it wasn't scattered or absorbed, and that would increase, would have a greater albedo because we are scattering more of this light. It's coming in, getting scattered all over, and then we're reflecting more of that heat out, which means less is being absorbed, more is being reflected back out, not absorbed. And the same thing with cloud coverage. The more clouds, clouds look white, and if you're looking down from above, they're scattering all that light back out before it actually makes it down to the surface. So those two things affect it. And then we need to talk about how do these things cause something known as the greenhouse effect, right? So the greenhouse effect, this is the warming of a planet due to its atmosphere. And so essentially what happens is heat from the sun is either absorbed or reflected based on the absorbed or reflected based on the albedo of the planet, or the emissivity, since we can, one determines the other. But it's based on that. The second thing, the greater the albedo, the more the light's going to get reflected off, and then that would cool us off. What happens is our heat, the planet itself, like the surface, is heated to whatever temperature it's at. Our planet's around 300 Kelvin, and then as it has heat, it has a black body radiation, and so it re-radiates. So heat is re-radiated based on the planet's temperature, like a black body radiation. Body radiation, and it's re-radiated back out. For Earth, this would be in the infrared range. So for Earth, this is in the IR range, the infrared range, which is, remember, this is red color. Red is the longer wavelength, and this is near red color, but it's a longer wavelength. Ultraviolet would be over at a higher frequency than violet color. Infrared is out at a longer wavelength than red, so this is a pretty long, low energy wavelength. So for Earth, it's re-radiated back out as infrared. Then, if the frequencies re-radiated, these frequencies, if re-radiated frequencies, if they actually resonate with gases in the atmosphere, then what will happen is, rather they'll be basically absorbed and then scattered back out. They will be absorbed, so they're absorbed first. This is important. They're absorbed first, and then re-emitted, I should say. Let me put it that way. re-emitted. They're re-emitted in all directions. That's important, in all directions. This means that some of this heat, so if we're looking like, let's say here's the surface of Earth, right? And here's the atmosphere. And so we have infrared coming back out, and it hits a little molecule there, right? So we have it hits a particle of gas here, right? There's these particles of gas there. This can be absorbed and then re-radiated out in any number of directions. So it's possible for it to be re-radiated back up out of the atmosphere, in which case the energy is lost. But some of this can come and hit our particle, a different particle here or something, right? It can hit a particle, and it can actually be scattered back down, re-radiated back down, because it can go in any direction at once, up, down, left, right, side, anything. So some of it will be re-radiated, will be re-emitted back out into space, and some of it will not. It'll be bounced back down. So the part that gets bounced back down and held in is basically just heat being held in, kind of like a big blanket, right? You get under a blanket, the blanket's on top of you, heat comes off of your body, right? Tries to get through the blanket, but it doesn't. It gets reflected back. So some of this gets reflected back down, while others gets on through and gets out. It's pretty evenly distributed. Just as good a chance for it to go in any direction as any other direction. It can go in, and basically it holds some of this heat in by doing this. Now, combining this with the argument for man-made global warming would basically be stating that CO2, carbon dioxide, it resonates with infrared. And so CO2, along with some other things like methane and stuff, but CO2 is the big one everybody talks about. CO2 resonates with this, and so CO2 would be one of these greenhouse gases. So this is the argument for man-made. Maybe I'll just put man-made global warming. Is that CO2 is one of these. Really hard to debate that it is, but it is. It'll do this. And so as we put more CO2 with our cars and stuff out, we put more CO2 into the atmosphere, then this effect gets increased. So it would increase this by a good amount depending on how much CO2 you put in there. And then you end up with this positive feedback loop where we start to, the planet warms, right? And then snow melts, right? And clouds turn into vapor and they stop being all white and like clouds. Snow melts. As snow melts, the albedo, right? The albedo decreases, right? Which means the emissivity increases, right? And if the emissivity increases, then we're absorbing more. Snow melts, albedo decreases, and then the planet warms. So the albedo, okay, so it warms even more. And if it warms more, then you just repeat this argument, right? So the planet warms, snow melts, albedo decreases and causes it to warm. If it warms, then more snow melts. And if more snow melts, the albedo decreases even further and it warms even further. So it's this kind of positive feedback loop that goes around. Now, this can also apply to something like a solar cycle increasing in heat. If the solar cycle goes up, then it's going to also cause the snow to melt and the albedo to decrease and cause warming kind of thing. So pretty much anything that can cause our planet to warm, the precession of the axis, the change in magnetic fields, the solar cycles, the the changes in eccentricity of the orbit, all these things that I've mentioned in past videos that you should look at, all these things could have this positive feedback. But the big question that is really hard to answer, that's really debated, is how much do each of these have of an effect? Is the majority of the warming caused by CO2, or is that the biggest thing that's causing the warming that we've seen, or is it a solar cycle? Is it just something natural? That's the big question, because any of these can have this positive feedback loop going on with this, and in all likelihood, what I would think is that it's a combination of all of these things. How much of a combination? I don't know. Is the CO2 1% of the warming? Is it 20% of the warming? Is it 99% of the warming? I just have no idea. And I don't think anybody really knows this point. No one has been able to tell us before, because our models just don't work so well at predicting what the temperature of a planet should be based on their atmosphere and how far they are from the sun. Last I ever looked at, our modeling failed pretty big on like what the temperature of Venus should be and everything like that. But what you need to know is that the man-made global warming part is because of this CO2 resonating with the infrared range, and then you need to know this positive feedback cycle where if the snow melts, the albedo decreases and causes it to warm, which causes the snow to melt even more, and so that basic loop will be something you're definitely going to need to know. All right, so other than looking a little bit through your books and making sure you've looked at some of the graphs and pictures that I am not going to draw out here, just so you're familiar with them, other than that, that's pretty much it for this topic. All right.